It's not about web anymore and has nothing to do with assembly. 5 years ago, Webassembly was set to make JavaScript for web browsers look miserable and slow, and now it appears that everyone's talking about how Webassembly will replace containers and Kubernetes. So what's going on? I've read a ton of articles and a bunch of papers, listened to a number of talks, and tested firsthand some of the most trendy WebAssembly technologies, all to answer the question, is it just another hype bubble, or should we really retire Docker and Kubernetes and jump onto this new train until it's too late? After watching this video, you will have a much better idea for which use cases WebAssembly is a real deal today, and of course you will no longer be puzzled by all these acronyms you could see online. As always, a bit of history to understand where it all comes from and why. Let me begin with the story of the ancestor of WebAssembly, SMGS. More than 10 years ago, engineers from Mozilla tried to squeeze every drop of JavaScript performance by building a new tool called Emscripten. Emscripten could take your C or C++ program and turn it into a super optimized JavaScript code. It achieved that by using JavaScript in ways that are known to perform better. The resulting cut-down subset of JavaScript was called SMGS. SM here stood for Assembly, a low-level programming language. With the idea of pushing the boundaries of what's possible in a web browser, SMGS was immediately used to port a bunch of good old DOS games. I live again. And even massive game engines like Unreal and Unity. Suddenly you could run Vim, SQLite, and even a bunch of open source desktop applications right in your Firefox or Chrome. This was possible because Emscripten, the tool that took your C, C++ code as input and produced JavaScript, went to great lengths to emulate a whole bunch of stuff that normal desktop applications expected to be available. From basic things like file operations to support for multimedia libraries like SDL. And mind you, all of that in a browser. Still, despite all the amazing demonstrations, the majority of people in the industry just didn't care. Maybe because SMGS was mostly focused on performance-demanding games development, or maybe because some of us have seen a very similar story already in the past, first with Java applets, ActiveX, and then with Flash. All these old technologies, just like SMGS, aimed for desktop-like interactivity for the web, while also promising solid security. And we all now know that these so-called rich internet applications were often used to exploit end-user machines because of serious flaws in browser plugins that were running them. So why SMGS and its next incarnation, Webassembly, got to be more trustworthy? To answer this question, we need to look into the design of Webassembly. With Webassembly, or WASM in short, you are not generating a highly optimized subset of JavaScript out of your C or C++ code like it was with SMGS. Instead, your program is turned into bytecode. Bytecode is like machine code. Machine code is a low-level representation of a program, the zeros and ones that a CPU actually executes. But bytecode is built to be executed not by a physical CPU, but by something that looks a lot like a virtual CPU. Such a virtual CPU is much more abstract than a real CPU because it's not tied to the details of how the hardware is built. And so is the bytecode. It's also more abstract than machine code. You remember the Java's motto, write once, run everywhere. Java programs are compiled to and executed as bytecode. You don't need to recompile your Java code for each CPU architecture you want to support. You build your bytecode once and it's Java Virtual Machine's problem to run it on concrete hardware. Same story with WASM. One bytecode to rule them all.
One ring to rule them all.
Okay, but it's one thing to generate bytecode and entirely different to run it securely. After all, notorious Java applets, ActiveX and Flash all use their own bytecode formats. The problem was with their VMs or runtimes. So how it's different with WASM? Because of the fact that WebAssembly grew out of SMGS, a JavaScript-based project, the idea of a sandbox was obvious. If you think about it, JavaScript in a browser runs in a restricted environment from the day one. You cannot just go read a file from a machine where a browser runs or talk to users' hardware like microphone or camera without explicit permission. The sandbox for WebAssembly is like that, but way more restrictive. By default, in Wasm sandbox, you can only do some basic math, perform loops, do some if-else branching, and not much more. You cannot even access the DOM, that is, the elements of a web page. This is the deny by default principle. Compare that to Java applets that can make network connections, open, read and save files, access clipboard and more, and all of that can be requested after the applet started executing, which of course makes security audit harder. Although you can run crazy things in Chrome, Firefox or God forbid Edge, from literally executing code snippets written in different programming languages completely on the client side to running LLMs, relational databases, this and even this Despite all of these wonders, WebAssembly today is not only about browser anymore. But how had this technology jumped from a niche for which it was initially designed for to a niche completely different to the server side? And what's more interesting, why? One of the design decisions behind Wasm bytecode was to make it streamable, which essentially means that Wasm bytecode has to be organized in such a way that a VM, a runtime, should be able to start executing this bytecode as soon as possible, without waiting for the whole Wasm module to be completely downloaded. Module, by the way, is the unit of packaging and delivering Wasm code. Think of it as of an independent Wasm program. So this feature, streamability, means that startup time for Wasm modules counts in microseconds, not hundreds of milliseconds, which is probably the best possible result for containers. Okay, so very quick startup time and a locked down deny by default sandbox. Someone at Cloudflare, a content delivery network company, took a note of these two features as early as 2017. This was the year when Wasm runtimes appeared in all major browsers. And this was also the year Cloudflare introduced WebAssembly support for their workers. Cloudflare workers are special programs that can be used to process requests coming to Cloudflare's edge servers. For example, workers can be used to filter clients based on some custom rules. Initially, these workers had to be written in JavaScript, but with the microsecond grade startup time and sandboxing, Wasm looked like an even better match for the use case. And let's not forget that without the need for a JavaScript interpreter, it should use less memory and potentially be faster. Cloudflare blog then recommended to use Wasm for resource-hungry operations like on-the-fly images resizing. As a developer, you were expected to follow the workflow of Wasm.js, write code in C or C++ and compile it with Emscripten, which now supported not only Wasm.js but also Wasm bytecode as a compiled target. Less than 2 years later, another CDN provider, Fastly, followed the suit, announcing their experimental WebAssembly edge platform Terrarium. Soon after, Fastly even open-sourced their own Wasm runtime, Lucid. Speaking of runtimes, there are now plenty to choose from. But are they just competing implementations of the same feature set, as it often happens in open source world, or is there a fundamental reason for such a diversity? To answer this question, I need to show you where and how people are trying to use Wasm. I already mentioned the first, historically speaking, non-browser Wasm use case, edge computing. A niche which is technically very close to Cloudflare and Fastly is API gateways. API gateway not only can hand over an HTTP request to a server that will process it, but can run some interesting logic before that handover happens. That is, for example, an API gateway can perform authentication and authorization, rate limiting, canary deployments, and so on. This is the reason why F5, the company that pioneered hardware load balancers at the dawn of the World Wide Web, bought a startup called Suborbital. Server-side WebAssembly, of course. And this is why software API gateways like Envoy or Kong support doing request processing logic in Wasm. So, for edge computing and API gateways, two things matter most. First, the runtime initialization speed, you remember, streamability, because thanks to it you can fire up the processing logic on demand for each incoming HTTP request, which also means that when the processing is over, You don't need an idling container consuming memory and CPU time, just waiting for the next request. This is scaled to 0. When there are no requests, no compute resources are used. What matters as well is the restricted nature of Wasm Sandbox, because in fact you just need to pass to the request processor, or a worker as Cloudflare calls them, an HTTP request related information as input and receive the same kind of data, potentially modified, back. On a conceptual level, if you will, it's a pure function, it has no side effects, and Sandbox is a bet that these side effects should be technically impossible. The best way to try Wasm for this use case is to install one of the many open source products with API gateway functionality. I will demonstrate Nginx compiled with a special extension that adds WebAssembly support. I also tested OpenResty, an excellent Chinese cousin of Nginx, for those of you who like to configure everything using Lua. You can also try Kong or Envoy. All of these products allow you to use the same proxy Wasm ABI, application binary interface, to interface with Wasm modules, which is quite useful because if it works properly, you can migrate all your Wasm request processing logic from one API gateway to another. Okay, so let me bring up the stuff for the demo. I need an extension called ngx wasmx. It supports different Wasm runtimes, and you need to make a decision at compile time. Here I will use the one called wasmtime. It's a runtime developed by the so-called Bytecode Alliance, which is a non-profit group of big tech companies and a bunch of startups. Bytecode Alliance considers themselves building a reference implementation of WebAssembly specifications. These specs, by the way, are maintained by the World Wide Web Consortium, an organization that was founded in 1994 and that is responsible for defining HTML, CSS, and a ton of other things. Wasmtime is used in Azure, Fastly, and it also powers the solution developed by the startup Fermyon. More on that later, when I'll show you how to run Wasm on Kubernetes. Instead of wasmtime, I could compile ngx wasmx extension with Wasmer, another popular Wasm runtime. I won't go deep in the woods of published performance benchmarks, because I really doubt that this can help you choose a runtime. What I think matters more is the following. Wasmer supports some specs which are not part of the World Wide Web Consortium's standardization work. I will share more details about it in a while when I explain how your Wasm code can interact with the outside world. Wasmer is used, by the way, in the already mentioned Kong API gateway, Service Mesh Software Linkerd, and by a handful of blockchain startups. Yes, blockchain smart contracts is yet another use case for Wasm. For my API gateway demo, I've tried a bunch of different example modules, code for which I found on GitHub. Not a single one based on C++ proxy Wasm SDK worked for me. I've had a lot of fun time with Bazel and Mscripton, and finally both Nginx and OpenResty report they successfully loaded all these test modules. But hitting corresponding localhost URLs did absolutely nothing, not even debug log messages appeared. All the build commands, makefiles, and configuration files are on my GitHub if you want to try to reproduce the issue. Until this moment I mentioned only C or C++ as languages used to write WebAssembly programs. But in fact, because Wasm is the bytecode format, if you can generate this bytecode from whatever source language, you will be able to run your programs on Wasm runtimes. And the most popular language for writing Wasm code is actually Rust. Rust is a complex language. It has a borrow checker memory management concept that is honestly difficult to simply grasp by reading a book. To internalize it once and for all, you need to get your hands dirty with more than just simple exercises. You need to get experience actually writing functioning software in Rust. This is exactly what codecrafters helps you to do. Sign up with my referral link below this video and start building step by step your very own Redis server, your own Kafka, or your own BitTorrent client, for example. There are many projects to choose from. Master Rust with codecrafters and start creating WebAssembly applications. For my demo, an example module written in Rust, which used the Rust proxy Wasm SDK, worked immediately. There is an entirely different computing domain where portability and low resource usage matter most: IoT. Building software for IoT more often than not means writing your C or C++ code for specific devices. Deployment to IoT devices usually means reflashing. The whole device firmware, which should now include your updated software, has to be replaced. And if this process goes wrong, you get a bricked device.
It's a brick with a power cord.
Wouldn't it be nice to have something like Docker containers here, so that instead of reflashing you just copy a new container image on a device? But containers are obviously too heavy for IoT, because you not only need your multi-megabyte container image, you need the container runtime, and for that container runtime you need a Linux operating system. That's far too much for embedded devices. But what if you could run something that is similar to containers in spirit, only with much fewer assumptions about the operating system and with far lower resource requirements? That would be awesome, right? But wait, there is more. What if you could write your code once and then deploy it to devices with different architectures? The only requirement is for these devices to have a WASM runtime. Sounds like all the pain in IoT development is solved.
Problem solved, yeah.
I figured out that there are two main WASM runtimes specifically targeting IoT. One is just like WasmTime, developed by Bytecode Alliance. It's called WASM Micro Runtime, and you can use it on these platforms. Not the slightest idea what some of them are. Anyway, another WASM runtime that is focused on IoT is Wasm3. What's interesting about it is that it functions by interpreting WASM bytecode. Other runtimes do AOT, compile the whole WASM module to a CPU native binary format before execution, or do the JIT, compile and recompile a program part by part during runtime, just like JVM does. Interpreting bytecode certainly makes Wasm3 slower than competitors, but on the other hand, it makes the code of the runtime itself simpler, and then in terms of supported architectures, I think Wasm3 is simply unbeatable. Good people, Wasm3 looks like a one-man project, and unfortunately currently it's in maintenance mode. Please read the details on the project's GitHub page, and if you can, support the project. Now let's jump to the next interesting WebAssembly niche, and it is unlike the first two. If for HTTP request processors in IoT, WASM is the place where the main application logic is, for this next niche it's different. WebAssembly is really just an extension method. If you want to provide extensibility, a plugin mechanism in your application, typically you would embed a scripting language interpreter and let your users write extensions for your application in form of scripts. Lua is one of the programming languages that is tightly associated with such a use case. But honestly, not many software engineers, outside of maybe game development industry, know or want to learn Lua. And even if you embed a JavaScript engine for extensions, JavaScript being way more popular than Lua, many developers still will not be covered. And again, WASM has something to offer here. Many compiled languages support WASM bytecode as a compile target. Old languages like Pascal and COBOL, and very modern like Zig and of course Rust. And you already know that it works with C and C++. All these languages require you to manage memory manually, and this is what you have with WebAssembly. When your module starts, you just get a contiguous chunk of memory, and it's up to you to make good use of it. If your programming language relies on a garbage collector, you either need to disable it, like Crystal does, or you have to bring your programming language runtime and put it in your WASM module. This is what Go does. As you may have guessed it, this is also how scripting languages work in WASM. They need their runtimes there. Of course, with a ported runtime, there's definitely a performance tax to it. Oh, and by the way,
guess what?
there's already a bunch of programming languages specifically designed for WebAssembly. Some of them look surprisingly like Rust. There is one mimicking TypeScript, and then there is also a functional programming language called Grain. Such a polyglot nature of WebAssembly means that if you would use WASM as a plugin mechanism in your application, theoretically you could cover a much broader developer audience with a wider variety of programming language preferences. This is what the creators of Extism framework are hoping for. You can import their open source library in your application. Extism claims to support a couple of dozen different programming languages, and then load WASM modules as plugins. Plugins can be written using these languages. If you think about it, such a plugin system allows you to mix and match libraries from different programming languages, combining their benefits. For example, you can take a regex library from Rust and use it in your Go application. In this demo, I will show you a wasm plugin written in C, which I will load in a Python script. The C program's goal is super simple. It needs to pick up a random entry from an array and return it. If you think about it, the so-called random numbers come from number sequences generated by a certain formula, and such a formula needs a seed number to start a sequence. For two different seed numbers, we will get two different random number sequences. So it's better for these numbers actually to not repeat ever. What's the solution?
Time. The answer is time.
Right. But the problem is that a system clock is outside a WebAssembly sandbox. Everything that in usual circumstances requires a syscall, like reading a file or creating a socket, is not possible inside a sandbox. And this is by design. If you want anything from the outside world, this should be done through communication between your module, the guest, and the host, the runtime that executes your module. Which means there should be an agreement, a specification on how and what exactly you ask from the host and how and what it will reply to you. Just like we have an agreement between the Linux kernel and the libc that syscall 169 will return the current clock value. In my previous demo, the role of such an agreement was taken by the proxy wasm spec. And you saw, by the way, that the C++ guest implementation of the spec didn't play nicely with Nginx host implementation, while at the same time Rust implementation was perfectly compatible and did what was expected of it. That is because the development of these different implementations appears to lack coordination. And we are talking here of just a single spec that the industry has come up with, the proxy wasm spec. Now imagine if different software vendors all create their different specs for their wasm use cases. This is exactly what has happened in the early days of Unix, when there were many different competing vendors and almost no compatibility between them. So at some point these vendors agreed on common standards, and now we have POSIX, that is a set of software compatibility standards that goes even beyond just Unix family of operating systems. When Wasm jumped from the browser to the server side, the need for something like POSIX became obvious. It had to be a spec that takes into account the very Spartan sandbox nature of WebAssembly and the fact that its bytecode is portable, so that requesting current clock value, for example, should work regardless if a runtime is deployed on Windows, Linux, or anything else. This spec is called WASI, WebAssembly System Interface. The creator of Docker said in 2019, if WASM plus WASI existed in 28, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. A standardized system interface was the missing link. Let's hope WASI is up to the task. So here's my simple C plugin that returns a random phrase. It uses WASI to get the clock value. And on the cooler side, in my Python script, I have to explicitly allow my Wasm plugin to interact with the host runtime using WASI. Here's how it looks like. Every single function that you want to call on the host side has to be requested or imported explicitly in your module. You can see how these imports look like by disassembling your module into WAT format, the WebAssembly text. WAT to me is some kind of a horrible procedural Lisp. So yeah, here's my clock call import. WASI is a slowly moving set of standards, and some people in the industry were not happy with that. So they came up with their own ideas of system interfaces. The already mentioned Wasm runtime is promoting WASIX, a standard which already supports threads, forks, and asynchronous runtimes, features you won't find in the latest WASI spec. Alright, so that was the plugin SDK Extism. If you work with JVM, you can extend your application with Wasm using Graal VM or Chicory. All the links, as usual, are on my GitHub, check the description below. Speaking of extensions and plugins, as of end of 2024, Wasm can be also used to write Kubernetes policies, eBPF programs, controllers for LLMs, these are programs that allow you to post-process LLM model output, and PostgreSQL foreign data wrappers. I've shown you the three big niches of non-browser WebAssembly: request processors, IoT, and plugins. They have very different needs, which explains the diversity of Wasm runtimes. But there is one more niche, and it's probably going to be the most massive. Since we already have sandboxed, quickly starting programs that we can code in many different languages, why don't we replace containers with them? Wouldn't it be great not to have to carry around all the distribution packages and libraries that require constant updates and trigger security scanner threat? With Podman and crun, you can run Wasm modules alongside Docker containers using the same familiar commands. Note that although I'm using a normal Docker registry, what I've pulled from it is not a Docker image. That's because an Open Container Initiative standard allows you to store different artifacts, not necessarily only Docker images, in normal Docker registries. There is a proposal for a new registry protocol designed just for Wasm, called WARG, but no implementation of it yet.
Maybe not today, maybe not tomorrow, but soon and for the rest of your life.
Now let me show you an interesting project that goes beyond just running Wasm modules using a container runtime. Fermion's Spin allows you to integrate your WebAssembly-based applications into an already existing Kubernetes infrastructure, while also providing a developer workflow I can totally enjoy. Let me install Spin and configure a new Python project with it. Let me show you the actual code. Spin up command, of course, allows me to work on my little WASM application locally, but as promised, now I will deploy the spin framework to run my quotes microservice on Kubernetes. Spin is an interesting attempt to bring WebAssembly to the cloud. It is designed for microservices and event-driven architecture in mind. If you have experience with microservices on Kubernetes, you will definitely be able to reuse the familiar mental models when working with Spin. But the next project I'm going to show you will probably challenge you, and it's a good thing. Wasmcloud does not try to fit WebAssembly as a technology into existing design paradigms. Instead, it tries to explore what's possible with its unique features. Right out of the bat, Wasmcloud even introduces its own dictionary. There are three main words: components, capabilities, and providers. Components are the latest addition to WASI, and they essentially wrap WASM modules with contracts that define inputs and outputs. When previously WASI was concerned about interactions between a guest, your WASM module, and a host, a runtime, components are about interactions both with the host and between different modules. Capabilities in Wasmcloud define abstract pieces of functionality that your component needs. For example, a key value store, login, or an ability to receive or send HTTP requests. Capabilities are added to a component's contract. And then you have providers. Providers in Wasmcloud are host plugins that implement high-level APIs of capabilities. For example, you can turn on Redis provider for a key value store capability and later switch to HashiCorp's Vault provider without changing your component's code. What will change is the contract, which is written in the WASM interface type language. As the Kubernetes folks among you may have already realized, the components capabilities provider's paradigm completely removes the need for sidecar and ambassador containers. And if you think about it, sidecars and ambassadors are in fact a workaround for a bad foundational abstraction, which is a pod. Okay, so now let me show you how Wasmcloud looks like from a developer's perspective. You can manage your local Wasmcloud application and configure certain things using the wash command, but the full control is possible with wasm.yaml. If you know what Open Application Model is, you will feel at home with the format of this file, but otherwise it's just another YAML file. You can also, just like with Spin, deploy Wasmcloud on Kubernetes. Good people, I have to admit that working on this episode demanded a lot of patience from me. Almost everything I've tested had its rough edges. Example code did not work, documentation often was nowhere to be found, and then weird behavior of some build tools resurrected an old sysadmin spirit in me. But, despite all of these hurdles, it was also a lot of fun, and in a sense, even eye-opening. If you watched my PostgreSQL video, you know that I believe our industry became too obsessed with unnecessary complexity. Somehow, operator for operators in Kubernetes is not a meme anymore, and architecture diagrams that are not fitting on the wall are considered something to be proud of. Server-side WebAssembly gives me hope that we, as an industry, can do better. From an energy-efficient version of function-as-a-service architecture to a less painful IoT development workflow, to an actually much better abstraction for modern distributed applications, all of that is WebAssembly today. Many things are still in the works though. To name one, there is no proper garbage collection on the runtime side, which makes Python, for example, not the best choice for WASM for now. The tooling for some programming languages is also not quite reliable, but implementation of ideas like component model is an absolutely amazing paradigm shift. It's like working with a functional programming language where side effects are clearly constrained after years of constant debugging of a leaking state. WebAssembly is worth the hype, if only because it makes us rethink the many design choices that we take for granted. If you have experience working with server-side WASM, please share your opinion. Thank you for your time and see you soon.